Meet two students who are on their way to take their exams. The first student turns left and takes one route to the examination hall. The second student turns right and takes an entirely different route to the examination hall. After a lot of turns, walking up and down, they finally reach the examination hall. Well, it didn't really matter which route they took because in the end, they both managed to get the desired results, which is to reach their exam hall on time. What mattered here was not the number of steps taken, but that the end result has been achieved. Does the same principle apply to chemistry also? Keep thinking. Welcome to today's show on thermodynamics. Today we will talk about enthalpy, a concept that is indispensable to thermodynamics. We will focus on the meaning of enthalpy and learn about enthalpy changes, that is delta H of chemical reactions. Define Hess's law and also learn about its numerical applications. Finally, we will discuss possible exam questions in Exam Decoded. The universe we live in is governed by laws that are absolutely simple. For instance, all chemical and physical properties are nothing but the exchange of movement of energy, that is thermodynamics. In chemical reactions, this exchange of energy is manifested as a change in heat that is either released or absorbed during the reaction. The significance of this statement for you as a student of chemistry is so great that I would like to show you an experiment that will make this concept absolutely clear to you. We have dissolved sodium hydroxide in water. What happened? We find that the temperature of the liquid has increased as a result of the reaction. Now let's see what happens when we put ammonium chloride in water. The temperature changes again, but this time it decreases. Now what's common to both reactions? That's right. Both are accompanied by a change in heat. The amount of heat released or absorbed in a chemical reaction is known as enthalpy and is represented by the symbol H. Now, enthalpy is an example of a state function. That means its value does not depend on the initial and final stages of a reaction. We can only measure the change in enthalpy. So, a change in enthalpy or delta H is measured as the difference between enthalpy of products and enthalpy of reactants at a constant pressure. And you must always remember that enthalpy is specified per mole of a substance in a balanced chemical equation. If we were to represent the function of enthalpy on a graph, it would look like this. X-axis represents the reaction pathway, which shows the amount of reactant being converted into its product. Y-axis represents enthalpy. In the first instance of the experiment we just saw, adding sodium hydroxide pellets to water led to the increase of heat. This, as you can see, is because the enthalpy of products was much less than that of the reactants. So delta H will be negative. Such reactions where heat is released and change of enthalpy is negative are known as exothermic reactions. In the second instance, we added ammonium chloride to water. Here we saw that the solution got cooler. The graph tells us that the enthalpy of products was more than that of the reactants. So, enthalpy change was positive and heat was absorbed. This is called an endothermic reaction. Let us begin with the enthalpy of those reactions where substances are in their standard states. That is, where they are in their pure state at 1 bar pressure and at 298 Kelvin. This is called standard enthalpy and is represented by delta H naught. Now, since there are many different types of chemical processes, there are also different types of enthalpies. Depending upon the types of reaction, we have enthalpies of formation, combustion, bond dissociation, phase change, and solution. Though many of these terms are self-explanatory, let's understand them one by one. What do we mean by enthalpy of formation? Well, when 1 mole of a substance is formed in a chemical reaction under standard conditions, the enthalpy change is called enthalpy of formation. In this example, the enthalpy change to form 1 mole of water is represented by delta H F naught. Here is a puzzle for you. In the given reaction, 2 moles of A2 react with 3 moles of B2 to give 2 moles of A2B3. Enthalpy change is minus 114.2 kilojoules per mole. What kind of reaction is this? And is this the enthalpy of formation of A2B3? Let's tackle this step by step. Observe the change in enthalpy carefully. It is negative, which implies that this is an exothermic reaction. Next, in the reaction, we find that 2, not 1 mole of product are being formed. So, this reaction is not an enthalpy of formation. Let us now look at a real-life example. In order to stop a fire, you need to cut off the oxygen supply from the atmosphere to it. And how do you do that? By using a fire extinguisher that cuts off the oxygen supply and causes the fire to die. Clearly, the access to a ready supply of oxygen is what aids combustion. Using this information, can you now define enthalpy of combustion? Denoted by delta H com naught, it is also called heat of combustion. If you have understood the concept of enthalpy of combustion, then here is a question. Given that the enthalpy of the reaction CH4 plus 2O2 gives rise to CO2 plus 2H2O is minus 890.4 kilojoules per mole, what is the enthalpy of the reaction 2CO2 plus 4H2O gives rise to 2CH4 plus 4O2? If you think this is a tough question, don't worry. Try solving it during the break and I will see you on the other side with the answer. Stay tuned. Welcome back. Before the break, I had left you with 2 equations and asked you to guess the enthalpy of the second one based on the enthalpy of the first. I had asked you, given that the enthalpy of the reaction CH4 plus 2O2 gives rise to CO2 plus 2H2O is minus 890.4 kilojoules per mole, what is the enthalpy for the reaction 2CO2 plus 4H2O gives rise to 2CH4 plus 4O2. It is a tricky sounding question but has a very simple solution. As you can see, the first equation describes the combustion of 1 mole of methane. The products in the second equation suggests that we should try to reverse the first equation. Multiply this by 2 to find out the enthalpy for 2 moles of methane in the second equation, and the final answer becomes 1780.8 kilojoules per mole. It is time now to talk about the next classification of enthalpy called enthalpy of bond dissociation. What happens when 2 substances react with each other? There is a breakdown or dissociation of bonds. When this happens, there are changes in energy or enthalpy. Strictly speaking, enthalpy of bond dissociation is the energy required to break 1 mole of chemical bonds in the gaseous state. It is denoted by delta H D naught. Now, we know that a single substance can contain many different types of bonds, each having different enthalpies. So, it is more common to talk about mean bond dissociation energy. For example, consider a molecule of methane with the following bond dissociation enthalpies. CH3H delta H D naught is equal to 432 kilojoules per mole. CH2H delta H D naught is equal to 469 kilojoules per mole. CHH delta H D naught is equal to 422 kilojoules per mole. CH delta H D naught is equal to 339 kilojoules per mole. How do we then calculate the bond dissociation enthalpy for the whole molecule of methane? Since bond dissociation involves breaking of 4 CH bonds, we do a summation of the dissociation enthalpies for all the 4 steps and divide it by the number of carbon to hydrogen bonds, that is 4. Another important chemical process involving the release or absorption of heat energy is phase change. When substances change from solid, liquid or gaseous phase into another, they register an enthalpy of phase change. Enthalpy of phase change is defined as the enthalpy when 1 mole of pure substance changes its present phase. These values are represented differently depending on the type of phase change. Enthalpy for solid to liquid change is delta H naught fusion. It is important to remember that enthalpy remains the same within a particular phase change. Example, enthalpy for a solid-liquid change is the same for its reverse, that is, for the liquid-solid change. Therefore, enthalpy of fusion is equal to enthalpy of freezing, enthalpy of sublimation is equal to enthalpy of deposition, enthalpy of condensation is equal to enthalpy of vaporization. Yes, even this chemical process of preparing a salt solution involves enthalpy. More specifically, enthalpy of solution, which is denoted by delta H naught solution. Well, we have discussed all the possible classifications of enthalpy and seen how important it is to consider them when working with chemical reactions. In fact, any chemical equation which includes a representation of its enthalpy is known as a thermochemical equation. Let's take a look at the thermochemical equation for carbon dioxide's formation. If you were to light a bonfire, then there would be 2 critical chemical processes at play. One would be the direct combustion of the dry leaves to form CO2, and the other being indirect combustion in 2 steps, which first leads to the formation of carbon monoxide and then carbon dioxide. Now, if you compare the thermochemical equations of both types of combustion, you will notice something very interesting. Although both form CO2 by following 2 different paths, their end result is the same. Not only that, in the first equation, we see that it is minus 393 kilojoules per mole. In the second, if we add the 2 enthalpies, we see the total is also minus 393 kilojoules per mole. So what does that tell us? No matter how many different ways or different steps there are in the formation of carbon dioxide, it does not affect its net enthalpy change. So you see, just as in the case of the 2 students taking 2 different routes to the exam hall that we saw at the beginning of the show, in chemical reactions as well, the end result is the same even if the paths or steps involved are different. And this is exactly what Russian chemist Germain Hess discovered in 1840. Known as Hess's law, this principle states that heat evolved or absorbed in a chemical reaction is independent of the number of intermediate steps and remains the same. From Hess's law, we can derive that the enthalpy change as a whole is equal to the sum of the enthalpy changes of all the intermediate steps. Okay, now I am sure that you have become acquainted with Hess's law. We have a caller with a query on it. Let's see what it is.
How will you find the enthalpy for a target equation when 2 other equations are given? What to use when?
There is no shortcut to it. You have to do it by solving. We will solve one right now for you. Let's determine delta H for 2NO2 plus half O2 giving rise to N2O5 from the enthalpies given. To solve the numerical, you need to use the information from the two equations. N2O5 gives rise to 2NO plus 3 by 2O2. Delta H is equal to positive 223.7 kilojoules per mole. This will be equation 1. NO2 gives rise to NO plus half O2. Delta H is equal to minus 57.1 kilojoules per mole. This will be equation 2. Enthalpy change for the two reactions are 223.7 kilojoules per mole and minus 57.1 kilojoules per mole respectively. Since we need to find the enthalpy of formation of nitrogen pentoxide, we must bring it to the product side. So, the first step will be to reverse equation 1. Reversing the equation will also affect the sign for enthalpy change, that is delta H, and it will now become negative. 2NO plus 3 by 2 O2 giving rise to N2O5 will result in delta H minus 223.7 kilojoules per mole. Number this equation as number 3. Next, multiply equation 2 by 2 because according to thermochemical equation in the question, we need 2 moles of nitrogen dioxide. 2NO2 gives rise to 2NO plus O2. Delta H is equal to minus 114.2 kilojoules per mole. This gives us equation 4. On adding equation 3 and equation 4, that is 2NO plus 3 by 2 O2 gives rise to N2O5. Delta H is equal to minus 223.7 kilojoules per mole. 2NO2 gives rise to 2NO plus O2. Delta H is equal to minus 114.2 kilojoules per mole. Enthalpy change of the reaction is equal to minus 337.9 kilojoules per mole. We get minus 337.9 kilojoules per mole as the required enthalpy change. You must be very careful about the stoichiometry of the equation while solving numericals on enthalpy. For example, if you had not calculated enthalpy for 2 moles of nitrogen dioxide, you would have lost precious marks. With that numerical under your belt, I am sure that you will be able to solve more of these questions in your exams. And just in case you feel a little underprepared, meet me after this break for Exam Decoded. Stay tuned. Welcome back. Like I had promised, we will now look at some tips and strategies to tackle those tough questions from the exams. To begin with, let's do a revision of the key concepts that we have learned today. We learned that enthalpy is the heat content of a reactant or product. In endothermic reactions, energy is absorbed. In exothermic reactions, energy is released. We also learned about the different classifications of enthalpy, and finally we saw how Hess's law of enthalpy changes could be used for various calculations in reactions. Now let's begin decoding those exams. Welcome to Exam Decoded, where we show you how to tame those exam questions and make them work to your advantage. If you think you are up for a challenge, then join me for the rapid fire round. I have 5 questions for you, either multiple choice or true-false type. You need to answer them in 5 seconds. Give yourself a point for every right answer, and you can see how you fared with our rating card. Your first question is, enthalpy is a state function. True or false? The correct answer is true, because it depends only on the initial and the final state and is path independent. The next question is, for exothermic reactions, enthalpy of reactants is greater than enthalpy of product. True or false? The answer is true. Moving on to the next question. Enthalpy change for endothermic reactions is negative. True or false? The answer is false. Here is your fourth question. Standard enthalpy of combustion is denoted by which of these symbols? A. Delta H naught C, B. Delta H naught I, C. Delta H naught F, D. Delta H naught D. The answer is A. Delta H naught C. And the last question for this rapid fire is, enthalpy is denoted by which of these symbols? A. E, B. T, C. G, or D. H. The right answer is D. H. Time now to look at the scoreboard. If you have got all 5 right, then you have earned the title of topper high flyer. A score of either 4 or 3 makes you an achiever, and any less than that means you are a learner. However, whatever your rating, it is a great idea to keep revising and practicing, and for that you can log on to www.topperlearning.com, where you will find practice tests, exam tips and more. After all, the idea is to ensure that you aren't just a high flyer on our rapid fire, but a high flyer in the exams too. Speaking of acing the exams, that's one area where all your abilities will be put to the ultimate test. The topic, chemical thermodynamics, has a weightage of 6 marks, which makes it critical from the exam point of view. And if you have been following the episode carefully, it would come as no surprise that numerical ability problems are the most commonly asked questions from enthalpy and Hess's law. In your exams, you can expect short answer type questions of 2 or 3 marks from this topic. Your question is, the standard enthalpies of formation of SO2 and SO3 are minus 297 and minus 396 kilojoules per mole respectively. Calculate the standard enthalpy of reaction for SO2 plus half O2 gives rise to SO3. In order to solve such a numerical, you must use the given data to achieve the target equation, which in this case is the formation of sulfur trioxide from sulfur dioxide. As the first step, you must write the equations for the formation of sulfur dioxide and sulfur trioxide respectively, as you have been given the enthalpies of formation of the two compounds in the question. Now, since you have to calculate the standard enthalpy of the formation of sulfur trioxide from sulfur dioxide, reverse equation 1. The enthalpy sign 2 will change because of this reversal. On adding this equation with the second equation, you will achieve the target equation of the question. Writing the equations correctly will fetch you half a mark per equation. Now, as the final step, using Hess's law, you must take the algebraic sum of the enthalpy of the steps of the reaction to get the standard enthalpy of the overall reaction. On calculation, your final answer will be minus 99 kilojoules per mole. This value, along with the unit, will get you the remaining 1 mark. Now, let's move on to the examination expert for useful tips to do well in your exams.
In the topic Hess's law of constant heat summation, while preparing for your examination, students, you should remember enthalpy of reaction, enthalpy of combustion, enthalpy of formation, and enthalpy of formation in standard states. Be careful about the sign of enthalpy change while writing thermochemical equation. Understand the numerical, apply the principle.
I am sure those pointers have put all of you who dread solving numericals at ease, and in case you are still a little unsure of yourself, then log on to www.topperlearning.com and practice to perfection. It is time for me to leave you now, but do join me next time. For, as the famous astronomer Carl Sagan once said, somewhere something incredible is waiting to be known. See you next time.